Hey, good evening, everybody. This is No Smile John with Disruptive Weather, and today is March 12th, and it's about 7:30 p.m. And what we're going to be covering today is a disruptive scientific thought. I'm not saying it's proven statistically. I'm not saying that it is absolutely what is occurring, but just questioning, throwing the idea out there here on social media. But before we get started, every time I say disrupt tonight, instead of doing water, I'm gonna do this little like juice drink. I just feel like the water could really make me wasted later, so I'm gonna go with this uh less risky drink of juice instead of water. So that being said, I've said disruptive now 3 times. Okay, so now that that's done, on to the idea or theory that I've come up with on my own, and that is warm air occlusions with tornadoes. So, kind of interesting. So let's go ahead and look at some background information first that could go along with this theory. So here is a paper from, um, well, let me go back to the top and show its mobile mesonet observations on May 3rd of 1999. If you're not familiar with that day, I would recommend just Google searching or going into Chat GPT and Googling or asking Chat GPT AI about it. But it was a pretty good tornado day in Oklahoma. Um, it I think on record, actually I know on record, it is the largest tornado outbreak in Oklahoma state history. So it was a pretty good day. Unfortunately, out of all the days I chased that year, I chose to stay home on this day. Yep. So I missed out on all the action, tired of going out over and over and over and not seeing any tornadoes. So anyway, back to the point of this paper and why I'm referencing it here, and that is temperatures in the RFD. So there were 2 storms that they had the mobile mesonets make passes through the RFD region. The first was the storm that ended up producing the Moore Bridge Creek F5, and then the second one was a storm further to the west that ended up producing over 20 tornadoes itself. And one of the key findings of these mobile mesonet measurements was when they were looking at temperature and moisture in the RFD region. So, if you're not familiar, rear flank downdraft is just that. You have your warm inflow air, and then you have rear flank downdraft, which is air that's descending. And when the two meet, that's when you get the warm moist inflow air meets the RFD. That's traditionally the school of thought for tornadoes and tornado genesis. So if it's RFD, which is rain cooled air through evaporation, and it's descending because it's now been cooled, you would expect the RFD temperatures to be cooler than the inflow air. However, the measurements that they took here showed only small theta V and theta E deficits in the hook echo from those that were in the inflow region. Don't worry about it, what theta V and theta E are. Just understand that theta E is a meteorological measurement that we take to determine the temperature and moisture content in an air parcel in a given location. Theta V is if you were to take that same air parcel and remove and unsaturate it, what would it be? So basically, when you see small differences in these parameters, it's saying you don't really have much difference in temperature and moisture from that of the inflow region. So that only small changes were or deficits were detected. And baroclinicity within the hook echo was also weak. So just saying less than 1 degree Kelvin or Celsius per kilometer distance. So if the RFD is cold because it's been rain cooled, then you'd expect there to be much larger temperature differences over a kilometer in this case. So again, this is a good paper. I recommend you go back and read it. But yeah, small deficits in theta E and theta V, weak baroclinicity, proxy for temperature differential over a certain distance. So keeping that in mind, I've seen this in several radar presentations now, and I'm going to use the another Moore tornado, another EF5 in Moore, Oklahoma, but from 2013 instead of 1999. And what we're going to look at here are images from the Terminal Doppler Weather Radar located near the Oklahoma City airport. If you remember back to the beginning, I mentioned we're going to look at a new theory that I've come up with, and that is warm air occlusions. What that is that the hypothesis is the warm, moist air in the inflow region of the tornadic circulation, the supercell thunderstorm, gets wrapped all the way around the entire circulation to cut off any rain-cooled air that may persist from rear flank downdraft. And so in that case, all around the tornadic circulation is inflow air, and none of this RFD air even comes in contact with where the tornado has formed. Now, I want to clarify that this hypothesis, this theory, is based only on strong to violent tornadoes. I do believe you can get tornadoes from many different processes, including a rear flank downdraft rushing out, and where you have that rushing out and meeting the inflow that's moving a different direction, you can get shear vorticity or rotation right on the boundary of the rushing out air and the inflow air. And that can give you a circulation that could then get stretched by the updraft velocity. And that could give you some tornadoes, but I think most of my hypothesis is most of those are weak. So in this example, the reason this hypothesis has come up is one, that paper by Markowski, again, a great paper. And so looking at this radar image, what I want to point out is you see here's the supercell thunderstorm denoted by higher reflectivity, heavier precip, denoted by these brighter orange and red and yellow colors. Down here in Moore, you see almost no precip. You see light green, some light blue, but relatively no precip whatsoever. And if people recall, this tornado was very visible without a lot of rain around it, so that's consistent with what was visibly seen at the ground by storm chasers and locals that videoed the tornado. This is classic. You see this a lot in supercell thunderstorms where you have this area of no precip or very little precip, and this is where the warm inflow air coming from the southeast comes up into the circulation. So all this air down here is warm, moist air that's getting pulled up into the supercell thunderstorm. So then, in theory, it would run into this hook or rear flank downdraft this precip in the hook echo, that's the rear flank downdraft region, and you get your tornado. But what I want you to see here is you see this relatively weak warm inflow air. I'm hypothesizing that this weakness in reflectivity here that you start seeing come in here and going down around on the west side. That's the tornado right there. That higher reflectivity there is debris associated with the tornado. But out here you see this green curling all the way up here onto the east side of this tornado. Goes all the way around and back to the east side. So that's what I think is happening is you're getting this warm inflow air and it just goes all the way around the entire circulation and cuts off any rain-cooled air from the RFD. So what is happening in this theory to get the hook echo? Well, my theory on the hook echo could be one of two things. You have the updraft, which tilts with height to the northeast or east typically. And you have precip that's getting blown away from the updraft by the upper level wind since it tilts. And that whole tilted updraft is rotating. So part of the theory is that you're having some of the precip getting wrapped around by the updraft just rotating. Some of it gets trapped out here, but you have the hypothesis is in the updraft, you have a diffluent region that is where air can go like this around and then out, and then some air goes like this and it spreads out, but you get this precip coming around. Imagine just a stirring rod in a fluid. You're stirring the fluid. But you have two different fluids here. One is rain fluid, where rain and precip are falling, and the other is where you have no rain and precip falling, and you stir it and you get them spiraling together. So that's one possibility. The second is if you have this warm inflow air coming in here and then rotating around as it goes into the updraft, that maybe you get some sort of boundary where that air is coming around, but then you have air that's not moving the same direction as this air, and you get convergence, and that causes a little precip line right where that convergence zone is. Not sure, just throwing hypotheses out again. But in the first scenario, one thing going back to that paper on mobile mesonet observations, they said that the raindrops in the hook echo were just large raindrops, not some of the smaller raindrops, etc., that you might see. So, again, just the hypothesis that you get this warm air in the inflow region that just goes all the way around and then curls to the east side of the circulation, in this case, a large tornado. So I'll just play this and you can see how that it does that. I'm going to pause it at another frame. You can see, look at that, that clear, that same color as the air there coming right around. And let's go forward to this time. Still see it. There it is. And then finally it gets into like more where there's a lot of structures and debris and it just throws debris around. Plus at this time it was starting to get a little bit more rain wrapped. But interesting nonetheless. And this is not the only storm I've seen this with. Look at that image. You can really see the green going all the way around. You even see it like up almost to the northeast side of the circulation. So pretty interesting. I Again, I'm hypothesizing that the reason that the mobile mesonet in this region was measuring the same type of temperature and moisture as the inflow is because they were still in inflow air that had been wrapped all the way around and basically cut off the tornado to be all warm inflow air surrounding the tornadic circulation. So Anyway, just wanted to throw the hypothesis out there. Again, I haven't done any other studies other than looking at radar here. There may be more to be learned from mobile radar. So I may, start looking at some mobile radar images and talk with some of the people that do mobile radar sampling of these storms and see if they see anything that might be consistent with this hypothesis. But nonetheless, it is pretty interesting. Well, since we're talking about this May 20th, 2013 storm, for those that don't know, my house was located right in this tornadic circulation at this time. I will show you some photos that were shared on Facebook. So this was a tornado, a picture of the tornado. This is my back door. This is metal right here. And my back door faces south, and my house was south of the center of the tornado. So this, you can see here, that's a 2x4 that was punctured through the metal door. To get this piece of wood out of the door, we couldn't pull it back out. We had to push it into the house. And then we went to cover this hole up with blue tarp, and we tried hammering nails into the metal, and we couldn't get the nails in. So I just had to stuff a towel in there. But meanwhile, a 2x4 was moving at high rates of speed, was able to just go through the metal no problem. So, um, this is my bed. I managed to sleep through this tornado right here. Just kidding. I did not get to sleep through the tornado. I was actually at work. I was not even storm chasing this day. So, kind of ironic. I'm finding a pattern here. Big tornado days in Oklahoma and John's not chasing. Interesting. Not saying I'm not superstitious, but anyway, you can see here's a big piece of wood, 2x6 maybe, that goes through the back side of the house and then goes into the corner of the house and then punctures through the wall again on the side of the house. Um, this the windows were all blown in, so all this is trash. I have to throw all this away because it has glass shards everywhere. Uh, there's a picture of the side right here. You can see all the broken glass and debris and everything that came into the house. Now, just down the road from my house, about maybe 100 yards away, this was a brand new house that was just finished maybe the previous week. This was a Monday that the tornado hit, so this was the week before. They had just been the new builder in the neighborhood was just finishing building this house. They hadn't even closed on it yet for sale. It was under contract, but it had not closed for sale yet. So nobody was living in it, thankfully, but you can see all that's left is a foundation. You can't find any of the house anywhere. This is a front look at my house, just to kind of give a vantage point. This is the north side. So every day when I was walking out of my house to drive to work, I got to see where the F4, maybe even F5 damage occurred just 100 yards to my north every day. Pretty emotional driving through that every single day, going to and from work. This is a picture of that piece of wood that went through the corner of my bedroom. You can see my gate has been disrupted a little bit. Just said disrupt. This was a disruptive tornado for sure. So, man, definitely not getting wasted as fast on this drink as I do with water. And there's a close-up of that piece. And this was another house. So this is a cul-de-sac right here. And the house that this is a house that's between the house that had nothing left and my house. My house is up here in this vicinity. You can't see it at night as well. By the way, it took me almost 5 hours to get to my house that day. So as you can see, this is another house completely destroyed, but there's at least a pile of rubble in this location. So it got destroyed, but not fully swept clean of its foundation. Okay, so that's all I have for today. I just wanted to throw out this new disruptive hypothesis that I came up with, which is warm air occlusions around tornadoes. Thank you for watching today, and if you like this video, please give a thumbs up. And also, I ask that you subscribe to my channel if you haven't, especially if you want to find some of these kind of outside the box ideas that I sometimes come up with, as I would call them, disruptive scientific thoughts. They're not necessarily always right, but they are just being thrown out there as new hypotheses based on some things I've seen and noticed in papers published. So that's all. Have a great evening, everybody, and we'll see you again soon.